I've actually finished my lectures. Benny's going to be taking over for lectures, but I wanted to come partly to introduce him. This is Benny Yoshida. He'll be giving the rest of the lectures, but also to say some administrative stuff. So the final project is going to be due at the end of class, the last lecture, March 29th. And the last lecture will actually be you guys presenting your projects. We'll have to work out the time, but probably 20 minutes or so is an appropriate length. And then you'll also turn in a written version of the project. So I've put in some information about it on the class webpage. So you should definitely start to think about what topic you want to do. We put together a list of suggestions, which is on the course webpage. Something related to error correction and fault tolerance. So this is just a list of ideas. You don't have to do one of those things if you have something else you want to do. Try to pick a topic by March 1st. And once you've done that, email me or Benny. And first of all, we'll tell you if it's OK, if it's not one of the ones on the list. And then at some point, we'll do a negotiation with you so you can figure out what research papers should be covered. So the idea of the project is you'll take 1, 2, 3 research papers, depending on how big and complicated they are, and kind of synthesize the ideas in them and write them up for the write-up and to present. OK? Is that clear enough? Yeah.
So we're not expected to do any original work?
No. I mean, if you want to, that's great. But that's not required now. And so while I'm here, are there questions on stuff that we did last week or before? OK, that's good. Then I'll turn it over to Benny.
Okay. Okay, so let's get started. So, hi, so I'm Benny Yoshida. So I'm a new faculty started last June. So this is a course on quantum error correcting code, if I understand correctly. And then, so I will, of course, teach quantum error correcting code. But I guess one probably big difference from Daniel's part and my part will be, I think Daniel is one of the people who actually invented quantum error correcting codes. But I belong to a generation who already, like, quantum error correcting codes existed. So the way I understand quantum error correcting codes and how they are developed, it's pretty different. And then, so I think it will be interesting to have like 2 separate viewpoints and so on to have some bigger picture on quantum error correcting code. And so, so I think one thing I should mention is that next week is like a reading week or something at the UW. So then we decided not to have a lecture next week. So just to make sure. Okay. So the tentative plan of this lecture is, so today I'm going to talk about the so-called toric code and its properties. And then we will discuss this property of the toric code in detail from various aspects. And then in the next lecture, we will probably discuss something called color code, which is something a little bit more complicated than toric code. But this subject is very important in connection to the fault tolerance. Then the next we will go further into a more generic theory of quantum error correcting code, which has a local support. basically, this local code is something which you can physically realize with some local Hamiltonian. And then I was encouraged to talk about some relevant topics which are kind of related to quantum error correcting code and something new. So, so in the final part of my lectures, I'm going to probably talk about the phenomena called the scrambling and quantum error correcting code. The scrambling is very, very roughly speaking how localized information get entangled with other systems and bigger systems, and then you start to lose the information about initial states. And then this idea has been applied to physics of black holes and so on. So that's something I wish to cover. But honestly, it's my first time to give 3-hour lecture, so I don't know how far we can get. And then also I prepared some material, but I'm not sure if it's too much or too little. Hope it's too little, right? Yeah. But anyway, so that's the plan. Okay, so let's get started. Okay, so again, we will talk about quantum error correcting code, but I think this is very basic, but it would be nice to recap what was classical code, but from physical aspect. So one prototypical example of a classical code is, of course, the so-called repetition code. And this repetition code just encodes one bit of information, 0 and 1, into repetition of zeros. And repetition of, oh no, it's 0. Ones. So that's simple. And why is this a good encoding? That's because suppose that our initial state is this O0 state. We encoded the information 0 into this one. Then suppose that, well, someone comes and then flipped my bits from 0 to 1. Then I would get something like 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, something like that. But the point is that if this error is not fatal, in a sense that error acts only on a finite number of spins or finite number of bits, then by basically looking at, like, by counting the number of zeros and ones, we can reliably recover the original information. And in this case, there are more zeros than ones. This means that, okay, it was probably O0 state. So here we have some error acting on code word, and then we have some recovery. And in this case of the repetition code, this recovery strategy is just a majority vote. And of course, this works well because this 0 state and 1 state are very different from each other. And then a more rigorous way of saying it is that their Hamming distance is n, where n is the total number of bits appearing. And the Hamming distance is just a number of different entries between these code words. Okay, so this is the repetition code. But we can actually interpret this repetition code in a more physical language as a Ising ferromagnet. Even more in a physical or more practical words, it's just magnetic hard disk drive. That is, we have the Hamiltonian with a bunch of qubits or spins. And this Z is Pauli Z operators. Then let's think about this simple Hamiltonian, where for nearest neighboring spins, we have these ZZ interactions. And you see that this ZZ interaction favors my neighboring spin to be aligned. So because of this reason, this Hamiltonian has two ground states. One ground state is, of course, all zero state. And the other ground state is, of course, all one state. So in this sense, this ferromagnet or Ising model is a physical way of encoding this repetition code. So in this case, ground state equals to odd world space. And essentially, this is how we encode information into our laptop and so on. It's a magnet. Okay, so this is the idea of a classical code. But we have probably already learned that quantum repetition code does not exist. And this is basically due to no cloning. So it just says that given this psi quantum state, we are not allowed to apply any linear operation which does this. So this is prohibited. Therefore, in order to protect quantum information, we need to come up with something more non-trivial. Okay, but one thing I want to emphasize is, of course, given this repetition code, classical code, there is a Hamiltonian whose ground state is a code word. Now, the similar idea here, we want to construct a quantum error correcting code whose ground state, we want to have some local Hamiltonian whose ground state space is a good quantum error correcting code. And this is the so-called toric code. Okay, so now I'm going to give you a definition of the toric code. And since we will be talking about the toric code throughout this lecture, so maybe I think actually I should probably use this board and keep this board. We shouldn't erase this board, so let me. Do it here. So for now, maybe I can just. I'm making a mess. So what is toric code? Well, toric code is defined on a two-dimensional square lattice. Like this. And qubits are placed on edges of the lattice. I guess I can stop here. And let's say this is a L by L lattice. And we are going to put this lattice on a torus, in the sense that, torus is just this donut. But the important thing is that this boundary is connected to this part. So if you go in this direction, you appear from here. If you go in this direction, you come back here. So let me. So this means that this line should be identified with this one, this one, this one. Now, just by simple counting, we notice that there are total 2 times L square qubits in this system. Now I'm going to introduce one Hamiltonian, which is the following. The Hamiltonian has two types of terms, which is often called the vertex operator and the placket operator. AV and BP. An AV operator is a four-body term, which is a tensor product of power x operator on these 4 qubits. So the way it works is we pick some vertex, like these points, and then we apply x operator on these neighboring qubits. So this is the vertex operator. And another one is the placket operator, BP, which is, well, we pick faces. And then P is the level of the placket, and then this is a. So what we do is we look at all the vertex and all the placket, and then define these operators. And then we say that this is terms in the Hamiltonian. This is how the toric code is constructed. Okay. Now let's study the properties of this code one by one. So, but is there any question about this definition of the code? Hopefully it's clear. Now, since we are claiming that this is the quantum error correcting code, the system should be able to encode something. So we first want to find all the ground state of this Hamiltonian. In a technical term, it's called logical qubits. And first of all, one important observation is that these interaction terms, AV and BP operator, commute with each other. And to see this, we can just look at, well, when AV and BP are not overlapping, they of course do commute. But when they are neighboring with each other, they always share two sides. This means that each overlap gives you -1 sign, so it's in total, it's commute. And this is nice because every terms are commuting, which means that we can solve the model exactly. Now, this AV and VP are Pauli operators, which squares to identity. This means that eigenvalues are either plus or -1. So in order to minimize the energy, we should take all the eigenvalues to be 1. So if this is the ground state, psi is the ground state of the Hamiltonian, then it should satisfy the following constraint. Right? For all V and for all V and for all P. So basically, this is the information we have in order to solve this Hamiltonian. Now the question is, how many ground states do we have? And it turns out that there will be 4 ground states. And to see this, we do the following counting argument. Now, the total quantum states that could exist in this system is, of course, the following. In the Hamiltonian, this Hilbert space is 2 to the n. Right? But for each operator AV, we can choose eigenvalue +1 or -1. And then basically, if you pick eigenvalue +1 space, you cut the Hilbert space by half. Now, you see that there are in total L² constraints, right? because this constraint there are L square vertex operators. So you have freedom to choose plus minus 1 for all the L square, except that there is one global constraint which says if you multiply all the vertex operators AV, then you actually get identity. And then I think this is something you can easily convince yourself. But if you have vertex operator here, 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 then again they collide at the same location twice, which then you get cancellations. And if you multiply all the AV operator everywhere on the lattice, you get identity. And similarly for BP operator. Oh, it's not summation. This means that even though there are L square constraints, only L square minus 1 are independent. And similarly for BP. Now, as I said, each constraint cut the Hilbert space into half. So the ground state, which is of course all plus 1 eigenvalue state, is given by the following number. Times. Okay. But of course, n is 2 times L square. So if you compute this, then you get 4. So this is the number of ground state. So from this argument, you notice that this system encodes 4 states or 2 logical qubits into the degenerate ground state. So if you write the energy spectrum, then there will be 4 ground states, and then there are some excited states, but there is some finite order 1 energy gap which does not depend on the system size, which separates this protected code word space from the excited state. So this means that logical qubits. So this is how we could probably solve the toric code. But you notice that basically this similar argument holds for any stabilizer code. And just to recap, that the stabilizer code was defined by picking up the so-called stabilizer generators, SJ. I guess Daniel has explained this in detail, I guess. But the point is that given any stabilizer code, we can consider Hamiltonian realizations by writing down the Hamiltonian like this, because ground state will satisfy, which is exactly the definition of the code word space of the stabilizer. But of course, in practice, we are interested in stabilizer code. If we want to think about physical realization with the Hamiltonian, then of course this SJ operator shouldn't be that complicated, in the sense that, I mean, in this case it's full body interaction, it's fine. But if this SJ involves like 1000 qubits, then it's very bad. So we want to construct some good quantum error correcting code with low weight SJ operator. Okay, so we just found the number of ground states. But now, next, let's actually see that this is a quantum error correcting code. For this reason, for this purpose, we first need to find all the logical operators of the system. And well, logical operators of the stabilizer code is basically operator which commute with all the stabilizer operators, but acts non-trivially on the code word space. And if we look at this Hamiltonian with this stabilizer code, you can actually find it pretty easily. So I'm going to just write down all the operators here. And there are 4 of them. Okay, now okay, so some string like X and string like Z operators. Let me call it X1 bar, Z1 bar, X2 bar, Z2 bar. Okay. Now let us check that this satisfies the definition of a logical operator in a stabilizer. Now we can check that these operators X1 bar or Z1 bar commute with the Hamiltonian of the toric code because it commutes with all the AV operator and BP operator. So for example, this X string, it trivially commutes with AV operator because it's consisting of X operators. But if we look at Z operator, then Z bracket acts like 4-body operator here, for example, but the overlap is like 2, Z, 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 Z. Then -1 phase get cancelled. So this X1 operator commute with H. And similarly, you notice that the Z string operator commute with the Hamiltonian. This implies that all these operators, X, J bar, J is 1 or 2, and these operators preserve the ground state space because it doesn't change the energy. Now, in order to see that these are actually non-trivial logical operators, we need to see that they actually act non-trivially on these 4 ground states. And to see that, actually, it's just suffices to see that the commutation relation between these operators. Namely, if 2 strings intersect with each other, for example, this X1 bar operator, the vertical string, and also Z, a lateral string, then they anti-commute with each other. Right? Because they share X and Z only on one side. And similarly, you get this anti-commutational relations. But of course, this X2 operator commute with Z1. So it's easy. It's probably nice to see that the anti-commutation occurs only on this vertical pairs. Now, having these commutation relations, we can actually label 4 ground states in the following way. Well, 0 tilde. No. Such that G1 bar operator acts like a Pauli operator on the code word space with respect to this labeling. So this Z operator, G1 operator cares the value of this first qubit only. And then similarly for G2, cares only these values. And for X1 operator, it just flip the spin in a logical space in the following way. Maybe I can explicitly. Okay. So as you can see that these logical operators act non-trivially on the code word space or this ground state. And they have some non-trivial action, and then they act like a logical Pauli operators. This is acting on the second logical qubit, and this is acting on the first logical. Okay, now the fact that this logical operators are something non-trivial, something very big, it's not a local operator, is actually a signature of this system being a quantum error correcting code. But now let me actually concretely demonstrate why this toric code is able to correct errors. So for this purpose, I'm going to consider this, some weak form of the error, which is called erasure errors. So this is a very simplified noise model, but I think this is a very nice example to show the property of this toric code. So this erasure error considers the following scenario. Qubits in my system, in my lattice, will be lost during my experiment. Maybe qubits are flown from away from the trap or something. And then we assume that these qubits are lost with some probability p. So if p is 0.1, then basically we lose like 10% of the qubits randomly. So this is a noise model we are considering. And then question is, can we still recover the originally encoded information or not? And for this scenario, actually, you can prove a very simple error threshold. That is, if p is smaller than 0.5, then you are safe. And this 0.5 is actually related to the percolation threshold of this square lattice, related to the So this is a square lattice, and I'm not going to draw the grid because it's a bit cumbersome. But so let's remove qubits with probability p. Then, so these dots or these regions are, let's say, regions where qubits are lost. So I only have qubits only in this region, and then these are lost qubits. But the point is, if p is smaller than 0.5, and then it is more likely that these regions or clusters of lost qubits does not percolate the whole system. In a way that you can always draw some path which go through the lattice. Now, of course, there are some very unlucky cases. So this is a typical cases. Some unlucky cases where, I mean, this is a very unlucky case that you happen to lose all the qubits along this line. But this is extremely rare, right? Because p times p times p times p times p. This is extremely rare. In this case, it's bad. But the point is, in this typical case, there is such a path of the string. Now, if I have such a path of the string, actually we are able to retrieve the original information because I have just explained that logical operators are string-like, but in the toric code, these logical operators are deformable. For instance, this was my logical operator, but we know that in the ground state space, this vertex operator is like identity because it has +1 eigenvalue. So I can apply this operator to my string-like operator, and then still it does the same thing, same action on the ground state space. So let's say if I multiply this logical operator with this vertex operator here, then this will change the shape of my string like this. And now my string looks like this. But the point is that by applying this vertex operator, you can freely deform the shape of the string-like logical operator. For example, you can do something like, I don't know, something like this by multiplying, I guess, vertex operators here, 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 here. So these string operators are deformable. Now, in this erasure error, in these typical cases, we can find some wiggly path which go from the bottom to up, which means that if we can measure this operator, like string of x or string of z, then we are able to know that what was the original encoded state, even though these qubits are lost. And of course, you can make this statement more rigorous in a sense that these typical cases, there's no calculation. This probability usually goes like 1 minus exponential of some constant, which depends on p, and some power of system size. And the unlucky case is just something exponentially small. This means that the probability of failure, which is again these unlucky cases, goes to 0 as n goes to 0. For this reason, we say that the threshold of this erasure error threshold of the toric code is equal to 0.5. Okay. So hopefully this kind of a rough argument about this erasure error gives you some question.
Two questions. One, is it as n goes to 0 or n goes to infinity?
Yes, infinity. Sorry.
Okay. The second question is on the other board, or sorry, the board behind the one that you're. Can we construct any arbitrary shape that forms a loop, or are there only certain shapes that we can construct?
So the point is that this is living on a torus, and then the original string is actually living on a torus in the sense that it wraps around the torus. And then you see that just locally modifying the path, you can't unwind this loop. So this means that the weight means the number of support of this non-trivial Pauli. is always lower bounded by L, right?
Okay.
So from this observation, we can show that it's actually the code distance D of this toric code is equals to L, and code distance is basically the size of the smallest possible logical operator in the system. Now, this erasure error is, as I said, it's the simplest noise scenario because in actual situations, environment can do something even worse in a sense that, well, someone may come and then apply some unknown, let's say, Pauli operator X or Y or Z or some channel locally in various places. In this case, we don't know actually where this environment has acted. In this case, we exactly know where the error has happened because we know that where the qubits are lost. So in this sense, this erasure threshold is the easiest case. But it is also true that if the system does not have an error threshold in a sense of erasure error, then there is no threshold for the more severe errors. Okay. Yes. Okay, so hopefully I have convinced you. Yes.
Can I ask a question about that part? I guess you're going to erase it. So, like drawing an analogy between like some Hamiltonian and the, like the stabilizer. So that is good as far as the ground states are identified as the same as the logical states, but the excited states of the Hamiltonians would happen with different probability as compared to the probability of having a number of flips in that case, for example.
Right.
So we're not drawing an analogy the excited states and the errors.
So basically, excited states are states with errors, and
yes, but for example, in that case, when everything is interacting with each other in the ferromagnet, once we have more than a number of flips, then more flips here.
Sure. Then of course, there are some errors which of course completely destroy the information. And for example, if I flip all the spins, then that's a fatal error. But the point is that if the error acts on some only a finite fraction of the qubit or spins, then it is possible to recover the original information.
Right.
When you say qubits are lost, you mean lost?
Yeah, it's just lost.
The phasing channel is completely lost.
It just went somewhere.
Okay.
Yeah. So more mathematically, rigorously speaking, what we are considering is we have some state psi, and we apply a trace over all the lost qubits. Okay, so right, so this is why toric code is somehow good. Oh, I shouldn't erase this.
So can a Hamiltonian like that be identified for say any CSS code?
Sorry?
Can a Hamiltonian like this be identified for any CSS code?
Yes. Any stabilizer code you can think of it as a quantum error correcting code at a Hamiltonian.
Use the sum of all the stabilizers.
Right. But typically, SJ, this stabilizer generator, is very big and then it's very unphysical. So we want to be able to construct some local Hamiltonian. This locality is very important, I guess, because if we want to have a Hamiltonian which has this state as a ground state, then you should just define this thing, right? But this is cheating because this is highly non-local. So the problem is we want to be this, this H to be local. Okay, now let's briefly talk about sort of the physical properties of the toric code, because this physical property of the toric code is intrinsically related to the fact that this toric code is a very good quantum error correcting code. So for this purpose, I'm going to talk about the so-called string net picture. And when I say picture, it's more like a slogan or the way we understand the toric code. But we can make this statement very precise by actually writing down the ground state of the toric. So so far all the discussions are pretty abstract in the sense that we just define these operators and then so on and so on. But let's write down how the ground state would look like explicitly. Now, I'm going to make one claim. So one of the ground state. So there are 4 ground states, but I'm going to pick one specific one. And then one of the ground state can be written in the following way. Product. One means identity operator. Okay, so this is the claim. And of course, in reality, you need to divide by some like 1/2 to the n square root or something, but just let's forget about it for now, because it's not that essential. So the claim is that the ground state can be constructed by this object. So this product of V means that we multiply this 0 product state or 0 state with these operators. And since these operators commute with each other, the ordering does not matter. Okay, so this is a claim, so I should probably give you a proof. So in order to prove that this is a ground state, we need to show that these 2 equations are true, right? So how do we do that? Well, the first one is kind of easy because BP times ground state, this state, explicitly writing it, right? But we know that BP commute with every operator, so I can commute it through. Then okay, this is true. But now BP is just a tensor product of power Z operator. And when power Z acts on 0, it's just 1. So we can just get rid of it. Then this is. So the first equation is satisfied. Okay. Second equation is a bit more non-trivial, but it's still easy to prove. We just compute this object. But important observation to show this is that when AV operator acts on 1 plus AV operator, then of course this is AV plus AV square. But AV operator is just a bunch of Pauli operators, and if you square it, you get identity back. So this operator, if you hit it by, AV, it remains invariant. And by using this, you see that, I mean, maybe I should. This is just ground state. So these two equations are satisfied. Therefore, this is a ground state. It's actually in the problem set, you will probably use some trick similar to this one to compute the so-called topological entanglement entropy of the toric fluid. But anyhow, so we have written down one of the, yes?
Oh, sorry, for the second to last equality, so when we multiply AB by 1 plus AB prime, what exactly happens in that?
Oh, so maybe I should probably really like, maybe I shouldn't have realized it, but it's fine. A, B, so this is O V prime. So this is the object we wanted to compute. Now maybe we can explicitly write it like this. V prime, which is not equals to V. Right? Then now, yeah, and then this is just. Now, since we have some nice expression for the ground state, so let's stare at it for a while. So this object contains bunch of terms, essentially like 2 to the n terms, 2 to the L square, well, lots of terms. And one of the terms included in this product is, of course, identity operator. If we pick identity of each product with identity, if we pick identity everywhere except one of the vertex, then that's like every one operator. So it's vertex. If you pick 2 vertex, then something like this. So basically, this product is just summation of all the possible number of the product of vertex operator, right? Maybe I should plus here. Now, here the sort of initial state, we started from the product state, which is O0 state. So I mean, I'm not gonna draw all the zeros because it's gonna be ugly, but initially it's 0. And if I hit this product state by identity operator, of course nothing changes. But if I hit this product state with one of the vertex operator, let's say acting on this location, it's a Pauli X operator acting on these 4 qubits, and then Pauli X flips 0 to 1. This means that you will get 1, 1, 1, 1, X. These 4 qubits. And except these 4 qubits, everything is 0. Now, what about this guy? Let's assume that this V1 and V2 are neighboring. then you see that these 6 qubits are flipped because this qubit is acted by x twice. Now, here comes this stringnet picture. Because this is all the summations acting on the product state. This means that this ground state can be written as a superposition of all these kind of states. Now, we can sort of draw a picture. So this is the all zero state, so we don't do anything. But because we have 1, 1, 1, 1, which is like loop, so let's draw some loop. And why not? Like loop. Then the point is that these vertex operator creates like tiny loops at each locations. And the way they collide with each other, so they sort of got merged together. If you look at these terms, like product of 3 operators, 4 operators, and so on. Maybe I can do explicitly. For these 4 vertex operators, this will be the loop. But the point is this ground state can be written as a so this gamma is just a label of all the loop configuration. So this would look like and by loop I mean that we have 1 state. Then for other regions we have 0 qubits. And the ground state of the toric code can be written in this way. So you just basically consider all the possible closed loop configurations. Maybe I should set closed. And take a superposition of all of them. So in this sense, people call this toric code is like one of the simplest example of the string net because there are lots of string forming network. And this is actually a Z2 string because if 2 strings collide with each other, they get annihilated. So addition is like modulo. So the reason why this picture is kind of nice is that this picture gives us some topological nature of the toric code. So as I said, this ground state we constructed from this method is just a bunch of superposition of loops living on a torus, which are closed. But you see that by applying these local AV operators, you only create local loops, and you will never be able to wind the torus around. Or even if winding existed, the winding number must be 2 or 4, or it's even. But now if I multiply ground state with one of the string-like logical operator, which is X string, wrapping around the torus, then this will create a non-trivial loop winding around the system. So in this sense, by looking at this winding number of these loop configurations, you can tell the difference between these 2 ground states. So all these observations would probably tell you that this toric code is like one example of the so-called topological order. And this idea of topology and so on are very important in this discussion. Yes?
Can you show like the winding number for, so these ones have winding number 0?
Yes, because you can shrink it continuously.
So what would be like a winding number 1? So like that would be a winding number of?
Which one? Yes, this one, yes.
Okay, so what would winding number 2 be? 2 lines then?
Right. So then, if you don't put any constraint on the rule of loops, then it's like winding number 2 is like 2 loops. Winding number 3 is like 3 loops. But this is qubits. And then so intrinsically, this calculation should be done with Z2. So if 2 loop is like 0 loop. And that is because if you create loop locally, let's say by applying X operators, and then if I apply another X operator here, then because I acted this qubit by X operator twice, which is same as identity operator, so the loop disappears. So in this sense, this loop is actually a Z2 loop. So you shouldn't think as like really like a string of a like actual classical string, but it carries Z2.
Okay, so that's because it's their qubits. And if there were like a Q trig or stuff like that.
If it's Q-trig, then it will be Z3 loops. And if it's Zn or n goes to infinity, then you can consider more like lots of winding or something, winding and so on. Okay, so this is like a physical picture of the toric board.
So if you put, instead of the tensors of zeros, or something else, then you still get a ground state.
Right, so here the important thing is that this zero state is invariant on the action BP here, because if I commit, yes. But if you start from some other product state, some carefully chosen one, then you can go to other ground state. Now, okay, so we see that these two ground states have different winding number. But you see like this winding number is something very global in a sense that if you are some micro, like tiny living object living on this torus, like here, it's very difficult to tell the winding number. Right? I mean, we live in this global perspective, so it's easy to see the winding number. But we can only do some local measurement, then we really don't know if some string, so if we can, let's say, make a measurement only on this location, and then if we see some string like this one, then we don't know if this string will go further and further and wrap around the torus. In this sense, any local measurement shouldn't be able to distinguish these two ground states. And this intuition can be made more rigorous by this notion of the so-called local indistinguishability. So the local indistinguishability is basically the following. Let's pick psi from ground state, any arbitrary psi from the ground state. So in this case, there are 4 of them and they are superpositions. And we shall construct the reduced density, density matrix. And now, we are on a torus, but it doesn't need to be on a torus, but well, torus. We pick some local region, R. A local region, I mean that it's a region which can be shrunk into a point without any continuously. So there is no wrapping around the system. And then it turns out that in this case of the toric code, the following statement is true. Which is so this is a definition of the reduced density matrix, and this is a complementary region, R bar. And it turns out in the toric code. Does not depend on psi. So this is basically the statement of the local indistinguishability. And I believe that Daniel has explained the sort of the way of proving this statement for the stabilizer code. Basically, this type of the statement follows because you can prove this because no logical operator on R. I mean, on R means that the logical operator which is fully supported on R. And in the case of the toric code, we saw that this string-like logical operator can be deformed, but you cannot change the winding. Now, this local indistinguishability has a very important physical consequence in the property of the toric code. Which is basically the stability. Now, imagine that we have designed some, well, toric code Hamiltonian. But of course, we are not that perfect, so assume that there are some perturbation added to this toric code. And this V is some perturbation, and then we assume that V consists only of local terms, and the norms are bounded, and so on. And epsilon is some finite, but small but finite number. Then originally, we had 4 ground states. Which are separated from the excited state with some finite energy gap. In this case, actually, the energy gap is 2, some finite number. Now, we are interested in what would happen if we add this perturbation to the toric code. Now, I'm not going to discuss this problem in a full details or full mathematical rigor, but I'm going to give you just some hand-waving or heuristic argument. But the claim is the following. No matter what kind of local perturbation we add, there exists some finite value epsilon. So if epsilon is very small, in a sense that it's small but finite, then for such perturbations, the system remains gapped for sufficiently small but finite. So. And moreover, the energy exponentially small. So what would happen is that originally we had exact degeneracy for states. By adding this perturbation, so I think I should draw it more beautifully. Okay, by adding perturbation, their degeneracy may be broken, but only a bit. In the sense that, okay, we may have some deviations, but the point is that this will fit in some exponentially small window. And this energy gap still remains finite. So in this sense, this ground state space is sort of still protected. So in this sense, this toric code is stable against any kinds of perturbation added to the Hamilton. And this statement that the stability against perturbation was originally kind of the conjecture proposed in the studies of the so-called topological order. And, but this statement can be proven in the full mathematical rigor. And the rigorous proof was done by these three people, Ravi Hastings and Mihalakis. But I can give you one very heuristic argument by using the perturbation theory. So since this epsilon is very, very small, we can treat this term as a perturbatively, and then we can do the perturbation theory. And we can study the effect of this perturbation term on the ground state space. But the point is, any local operator V, well, V would consist of some local operator Vj. Any local operator cannot have a non-trivial coupling between ground states. That is because we need a string-like operator. So, okay, in the first order of the perturbation theory, we have this local term trying to couple different ground states, but it doesn't work. So we need to go to the higher order of the perturbation theory. And then if we go to the order L perturbation, where we start to look at the product of like V1, V1, V2, like order L terms. Then at the level at this higher order terms, you start to see some coupling between different grounds. And then only at that level, we start to have some non-trivial coupling between ground states, which induces some shift of the energy. But such a higher order terms are exponentially suppressed with respect to L. Therefore, this kind of argument should be. But of course, this is not a rigorous argument, because in order for this kind of perturbation theory and the perturbative expansion to remain converged, we need to take epsilon to be sufficiently small. But basically, this is the reason why the toric code should be stable against any types of perturbation. And this is a direct consequence of this local indistinguishability because any local perturbation cannot directly tell the difference between ground state. Okay, so right, so that's the local thing, and then so maybe I think it's good time to have some break, like 10 minutes break, so we can resume at 3:30. That sounds good. So we have been discussing properties of the ground states, but of course this toric cold Hamiltonian has a bunch of excited states, and then these excited states are also interesting. So how do we create an excited state starting? So suppose that you have a ground state of the toric cold. Then you want to go to an excited state, and then how do we do that? Well, so we have already seen that this string-like logical operator, string of x and string of z, commute with the Hamiltonian. Therefore, they do not change the energy of the system. But what if we prepare a kind of part of the string? So this is like a part of the closed loop, and then we cut, and then we have some. So it's an open string. Then what happens if we apply this operator to a ground state of the this toric code? Then you notice that this operator still commute with almost all the operators except these two operators. Because x and z operator anti-commute with each other. This means that this vertex v1 and vertex v2, originally eigenvalues were +1, but now eigenvalues are flipped, and it becomes -1. Right. Now, similarly, if we multiply kind of part of this x string operator, then it does not commute with this placket operator, placket P1, P2, because placket operator has z operator. Therefore, we will create an excitation because this BP constraint, BP1 and BP2 constraints are violated. So because we have two violations, so if we go back to the Hamiltonian, this means that this configuration has energy 2. This configuration has energy 2. Okay. But now, because this excitations is sort of localized here, in a sense that, well, energy is only existing here, and then each of them carries energy exactly 1. Well, it's actually, I said energy 1, but flipping gains energy 2, so it's actually energy 2, but well, it has some unit energy. And this anion is just a way of interpreting this excited states as particles. So important observation is that these excitations, this pair of excitations, can be viewed as a quasi-particles. Okay. Now, for some historical reason, violation of the vertex operator is usually called electric charge. And we use level E, while violation of the placket operator is usually called magnetic flux. But these names do not matter much. The important point is that we can view these excitations as two types of particle, E and M. So in this case, this is E, and in this case, this is M. Now, I think this notation could be confusing, so let me just make sure that this is related to E particle and this is related to M particle. And finally, we can also consider excitation. Which are created by both of an X operator and Z operator. So if I apply, maybe this is a bit confusing, so maybe some joint of an X string and Z string, then this will create excitation E here, and M here. And M here. So in this case, what we are creating like a joint object of E and M, as a pair. And this joint object is usually called fermion, and it actually obeys the fermion statistics, as we will see soon. So this is joint of E and M. Okay, and these names, electric charge and the magnetic flux, just comes from analogy to lattice gauge theory. But again, it doesn't matter much. So one observation is, of course, we created these elementary anionic excitations, this E particle, M particle, and so on. But the point is, starting from the ground state, you can basically reach all the eigenstate of the Hamiltonian by applying these Pauli operators. And so excited states can be interpolated in general as some configurations of E, E, or M, M, F, F, and so on. I'm sitting somewhere on the lattice. Okay, so now there are important properties about this excitation, quasi excitations, and I guess we should understand why these excitations are actually called anyons. Yes?
So for the fermion, is it just any electric charge and magnetic flux that they're beside each other?
Sorry?
For the fermion, is it just any, as long as it's beside each other, that forms one?
So they must be forming the joint object.
What if... Okay, so what if it's like one's perpendicular, one's parallel, and you have one fermion forming? Does that work?
Oh, I see. No, I understand. It still works, yes.
Does it matter how many electric charges and how many?
It doesn't matter. So let me proceed. So it's actually, yes, related to these two questions. So let me explain some of the key properties. First, these excitations must appear as a pair. And you see that these appear as a pair because, well, it appears on endpoints of a string, and the endpoint of the string, there are two endpoints, of course. But a more mathematically rigorous way of seeing it is the following. Remember that we had this constraint. Right. If we multiply all the stabilizer generators, this AV operator, BP operator, we get identity operator. Now, if I denote eigenvalues of these AV operator and BP operator for some state, this small AV and small BP, and then AV equals to -1 means that there exists E at V, right? And so on. And then means M at P. But the point is that if I multiply all these numbers, +1 or -1, for all the vertex, or the placket, we should get +1 because all these operators should multiply to identity. This means that the number -1 in this AV and also BP must be even. This means that the total number of electric charges or magnetic fluxes that could exist in this system is always even. So modular. So there is some hidden conservation law in this system. Now, another important point, which is actually related to how we create fermions and electric charges, this system is topological in the following sense. Here we have created this pair of E particle by, well, applying some straight string-like Z operators. Okay, but we could have prepared the same E particles by applying string operator like this. So they must be equal. Why? Well, the reason is if we multiply these two operators, what we have is a closed string of Z operators. But this is just acts as identity. So remember that more precisely what we are thinking about is this operator exists and we are implementing it into a ground state. And this is because this loop-like Z operator acting on ground state acts trivially on the ground state. And the reason is that this thing is a product of bracket-like operators. So it turns out that even though we pick some particular paths to create excitations, the way you create excitations and then prepare on some particular location, it does not matter. All these trajectories are deformable. Now, another important observation is that these stabilizer generators, what can I say? Yeah, it's kind of topological. And now the reason why this closed loop operator was an identity is just because it is a product of stabilizer operator, which means that this operator is within the stabilizer group. Now, if we think about the process of implementing these stabilizer operators, then first let's say we apply part of Z operator like this. Then we slowly grow these string-like operators, and then eventually, let's say, we close the loop. And then this is just stabilizer operator. But this kind of a sequence of time lapse has a physical interpretation. First, if we implement this segment of the string operator, we create M. Was it M? No, it's E. Yeah, it's always very confusing. E particle here. But by implementing and making this string larger and larger, basically what we are doing is we are moving this electric charge this direction. And then eventually these electric charges collide here, and then they get annihilated and becomes a vacuum. So this trajectory of stabilizer operators, like how you draw it, it's time lapse, has an interpretation as a pair creation. Because at the beginning you created pair of E and then bring it, and then propagation, and then eventually you annihilate these two particles. And you can use the same observation for the magnetic flux operators. Okay. So for these reasons, these kind of excitations do have some meaning as a particle, because like putting some particle here or here, like how you move it and prepare it here and so on, I mean, it should be equivalent, right? It shouldn't depend on, like, this particular state shouldn't depend on how you bring your particle. So these, because of these topological properties, the toric code and this excitation have some legitimate interpretation as quasi-particles. But as this name suggests, this is anion, and it has a very weird properties. So let me explicitly discuss why these excitations are called anions. Now, we are going to do two exercises, sort of. First, we are going to consider the following scenario. So you create some pair of electric charges, and then one of them is sitting here, and then you separate them, and then you prepare it here, and then there's another one here, but it's very far away. Then now we wind. So E winds around M particle. And if this E and M are just some ordinary particle, like some classical particles, then I mean, circling around it, it shouldn't give us anything non-trivial. But it turns out in this case of the toric code, we will get some additional phase factor, which is -1. And this process is called braiding. So braiding is just a process of one particle circling around another particle, like 2π rotation. Another thing we want to check is that this fermion, what we call fermion, is actually fermion. So we again prepare two fermion here. Then we exchange them, the locations. Then we want to see that we gain some additional phase factor. Okay. So this is what we are going to check very explicitly. And this one is a bit complicated to see, and then I'm not sure like it will be more appropriate to do it on the board, or you should do it by your hand. But this one is pretty easy to demonstrate. Okay. Let me use this. Now, we start from the ground state. So this is like square this grid. Then time goes like this. Then I'm going to construct some process which does this braiding of E on them. And let me draw lots of squares to show the dynamics. So now, at the beginning, there is no particle, so it's a vacuum ground state. Now, let's apply a bunch of X operators. This X operator will create magnetic flux. So basically, the process is like I created a pair of excitations here, and I send one of the magnetic flux in this direction. Now we have M and M here. We construct another string-like object, which is string of Z. And then this will create pair of E and then send E upward. So now we have 4 excitations But then now I'm going to undo the process. By doing this X operator again. Then this will send my M particle in this direction. Then I annihilate them. Then finally, I remove these pair of E particles. Okay. Then we go back to the vacuum. Okay, so what happens? So now from the perspective of, let's say, which one is good? Okay, from the perspective of this guy, this E particle, so for this guy sees E particle go in this direction. But then this guy sort of go in this direction, which means like it's actually, he feels like E has wind around M, and does it? I feel like it's a very bad explanation, but anyway, yes.
I guess I have a question. Like, what determines the direction of the arrow in each of these?
Oh, so it's actually, that's a good question. So in this case, it's actually, right, so this direction arrow actually it's there's no definite meaning. You could actually interpret it as a down arrow. And the point is that in this case of the toric code, it doesn't matter which direction you E wraps around M. So in this case, I'm like drawing as if E winds around in the clockwise.
Yeah.
But anti-clockwise, but it turns out you get the same phase in the case of the toric code. But this is not generically true. And in that case, we should be very careful. But in this case, we can safely assume that this is going in upward direction and so on.
I guess how would you formalize like a direction to go with?
Right. So in the case of a more generic theory of topological order, it's actually what we create is E and also anti-particle of E. And then E bar is actually not equals to E. So then, so these two processes are like upward or downward has two different interpretations. Moving E upward or moving E bar downwards. So it's very different. But in this case, we can interpret it like E going up or E going down. So it sounds same, but in a more generic theory, it's different.
I just have two questions. So originally it was his question, but then in the fourth square, so what did we do? We turned off the X operator? Yeah, that one. Did we just turn off the line?
Right. So basically, we apply X to move this M operator and then let this guy hit M and then annihilate.
Okay. So, and then the second question would be then why, it seems like the system is symmetric. Why would you have like
the system is symmetric.
Right, why would it have the, or is it just giving a different topological connection to the E bar and E?
So sorry.
So if you apply the X operator,
here
right?
or here?
Yeah, or anywhere. That's like a symmetric process. What is the operator? Why would you generate a anti-electron or the E bar and an E? Shouldn't they just be two E's instead?
Oh yeah, two E. Yes. But so this is again the artifact of the toric code, the system made by qubits. And then for more generic topologically ordered systems, so more generic quantum error correcting code such as qubit stabilizer code or qubit toric code, and this E and the other antiparticle are different particles. But in the case of this Z2, because in the case of Z2, I mean, it's like there are only two possibilities, 0 or 1. So that's the reason. And so that is reflected in the fact that making clockwise rotation, anti-clockwise rotation, it does not matter. But in the case of the qubit stabilizer code, this process does matter. So let me recap. So there is this freedom to of interpretation, like M is moving in which direction and so on. But the point is that the process we are thinking about is we create a pair of M here and then send one of the M into this direction. And then we create E and then send one of them in this direction. And then we annihilate M again and then annihilate E again. And then if you look at the relative positions, how they changes, then we will see that actually M, from the perspective of this M, E has wrapped around M. Well, I mean, it's the same, I guess. Now we have reached to we have went back to the ground. Yes. Okay, we have returned to the ground state, but it turns out that we have gained some additional minus phase factor. And then to see this explicitly, we just should write down all these processes very explicitly. So we started from the ground state, and now first we implemented this X string. Okay. We have implemented this Z string. Then we undo the process. And then we undo the process again. Okay, so this is the outcome. But the point is that these two operators anti-commute. So if I commute through this guy, exchange them, then what I get is -1 times this string times this string. I mean, this is just, they are the same object, so they multiply to identity. And yes, this is just minus. Okay. So this is the reason why if you grade E and M, then you get some phase factor -1. And of course, I have been discussing this with this particular straight line process. But the point is that on the way you create excitations, it's deformable. So you could have actually sent M particle in this way or this way. It doesn't matter. As long as this E particle wraps around M or M particle wraps around E. Yes?
But then, so for this, because the two operators, they don't commute, that's how we get a phase, right?
Mm-hmm.
But for the same excitation for M, since on torus, if the M line is like on that, so then it will commute with the pair of electron, this operator. Then you would not get this effect, right? So instead of the line X operator in the center, if you have it on the two edge.
Right.
So this will not have this commuting effect.
So what do you mean by edges?
Because this is on a torus, right? Like this. Is
Right. But okay, sure. But this braiding is a process which is happening like locally, right? So you have a very, very big system, and you have two particles, and you just exchange them. So in this discussion, I mean, it doesn't matter if the system is living on a torus or, I mean.
But so in this picture, if you connect the two magnetic flux through the edge.
Through the edge, yeah.
Yeah.
Then they get annihilated because it's a torus, so yeah.
Well, no, I mean without the center. You still have the same excitation.
Oh, you can create the excitation like this one, like
you would
from
not get the phase.
Right. That's because M hasn't actually wrapped around E. Right.
But so the core process is still the fact that the operators don't commute.
Right. So the point is that if in this case you see that this operator trajectory, they have some overlap, and then this overlap is very crucial to have this non-trivial winding. if we do your process, then if we look at like how their relative position changes and so on, then it's actually there is no winding happening. So that's why we don't have any additional phase factor.
So then would it be more correct to say the more fundamental what's causing this behavior is still the operators and their behavior as opposed to the magnetic flux? And
Right. So we need to actually carefully look at how we implemented like this string X operator and Z operators, and then sort of you need to imagine like three-dimensional picture. So X operator and then this something like time direction, and to make sure that they have some non-trivial winding, linking. Yes. And I guess this is, I think, the simplest way of seeing the braiding, because like this argument works for a very tiny region without looking at the global structure of the system. Okay. Right. So E and M particles are mutually sort of have a non-trivial braiding statistics, and now the fact that this F particle forms a fermion is a bit difficult to see. So I would really encourage you to actually sit down and then draw some figures and then do the calculations. But the point is that what we should do is we create a pair of fermions, let's say F1 and F2, and then we exchange them and then annihilate them again. Then we compute this path, and then we can verify that it's actually -1 phase is gained. And this calculation is a bit non-trivial because if you do this, there are two lines, like E particle lines and M particle lines. So this single line is actually like this two-line processes. Then one of the line goes in the like above and below and so on. Then you really need to carefully look at the trajectories, but you'll be able to carefully check that it's actually there is a -1 sign. So this is actually a way of checking that this F particle, which is a composite of E particle and M particle, has a fermionic statistics. Okay, so now, right, so we have been discussing toric code and also excited state. So we have also, in principle, explored like all the possible states arising in this toric code, but there's one still very artificial fact about this definition of the toric code. That is, of course, this is living on a torus. So, of course, it is practically very important to construct some quantum error correcting code, like the toric code, which can live on a system with boundaries, like without any having this non-trivial topology or something like that. But this problem has actually a very deep implications. This physics of classifying and constructing boundaries has a very deep implications about classification of anionic excitation in the topologically ordered system. But for now, let me just address this question of how to construct a toric code in a system with boundaries. Now, it turns out that this toric code has two types of boundaries, which goes by the name rough boundary and smooth boundary. And you will see why these names are used, because so here is the square lattice, but it's not living on the torus anymore. So these are actually physical boundaries. Now, there are two different ways of terminating this graph or this lattice. One way of terminating this lattice is this smooth cut, smooth line cut, and then the other one is rough cut, and this is rough boundary, and this is smooth boundary. And qubits are put still on edges of the graph. The following way. Okay. Now, on the bulk away from the boundary, we use the same Hamiltonian, like vertex terms and placket terms. But near the boundary, how do we define the Hamiltonian terms? Now, here's how we do. Near this smooth boundary, we have this object, like this object. Here we just demand that this is a 3-body X operator. Similarly, on the rough boundary, we have this object, this imperfect placket. Then we just put Z, 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 3-body Z. Now, it's kind of non-trivial, but you may check that these terms commute with each other. For instance, if you have XXX, this 3-body X, then they commute with this 4-body Z operator because they overlap with two sides. Similarly, if you have Z, Z, these 3-body operators, it should commute with this vertex operator because they are sharing two sides. So this is like a clever trick to construct a toric code, sort of the toric code in the presence of boundaries. Again, all the terms are commuting with each other. So it's again the stabilizer code. Now, we saw that there are 4 ground states in the toric code on the torus. But what's the number of the ground states in this case with boundaries? And in order to count the number of ground states, of course, we want to find all the possible logical operators. So let us do that. Now, okay. one of the logical operator would still look like this. This string of Z operators. And again, you see that this string of Z operator commute with all the Hamiltonian terms. But there is one important observation, that is, this is the boundary. And this Z operator sort of started out from this rough boundary. But the question is, can we terminate this Z operator on this smooth boundary? Then the answer is actually no. Because if we were to deform this ZZZ operator and then go in, let's say, in this direction, like this, then you see that this endpoints anti-commute with this XX operator. So this is not a good logical operator. So for this reason, we only have one Z-type string operator which go from a rough boundary and the end on the rough boundary. Similarly, one, two, three, four, five. X-like string. This X-like string can start only from smooth boundary. There is no way of ending it on rough boundary. Again, because it anti-commute with this operator. Now let's call this operator Z1 bar and then X1 bar. Now, of course, these string-like operators, which are starting from the boundary, is deformable by multiplying these stabilizer generators. But the point is that in the previous cases, we had like two types of string operators going in one direction, lateral and vertical. But in this case, we only have just one pair of string-like operators. And of course, they anti-commute. Now, if you carefully look at this Hamiltonian, and then you can, I think, convince yourself that these are all the possible logical operators, which means that there's only one logical cube, or equivalently, it's two ground states. Okay. Now, we have seen that this types of the string-like operators and these types of the boundaries are strong. There is some strong relations, and this relation can be nicely understood in the language of anyons. So previously on the torus, all the excitations or all anyons were created as pair excitations. Right? Namely, that if you count the total number of electric charges or magnetic fluxes, it was even. But in the presence of the boundary, this is no longer true. For instance, if we have lattice with boundaries. And if we pick these z operators and apply part of it, then again this z operator commuted with each other, and then if I prepare only part of it, then we are creating a single E particle here. Similarly, applying part of X operators, you can create M particles. Now, this phenomena that is breaking the sort of a conservation law of the anionic excitations, this goes by the name of a condensation of anions. But this is just a name. What it means that on the, let's say, this is rough boundary. We say that E particle condense. That is because we can actually create single E particle from the boundary and then bring it to the bulk. So single E particles. Similarly, we say that on the smooth boundary, M particle condenses, and then that is because we can create a single M particle starting from a smooth boundary. Now, I guess the one important question is, it seems that we can construct the two types of boundary, rough and smooth, where E and M condenses. Naturally arising question is there any third boundary? Where F condenses? And it turns out this is prohibited. And it turns out this is related to the fact that this F is actually a fermion. And I'm not gonna give you a proof in this lecture, but maybe I'll give it in the homework. But there is some mathematical argument you can make to prove that there is no such a third boundary where F particles condenses. So we have seen this phenomenon of condensation of anions or gapped boundaries of the toric code by studying this very simple model of the topological order toric code. But this phenomenon of condensation of anions have been a very central topic of researchers in the past several years, and the people have been classifying condensation of anions in two-dimensional topologically ordered systems and explicitly constructing gapped boundaries and so on. But more recently, it has been found that this phenomena of gapped boundaries and condensation of anions are closely related to the fault tolerance, such as transversal gates and so on. Yes?
So the condensation effect is just the sense of creating one.
Mm-hmm.
What happens if you just created one E and one M right beside each other? Do you get a fermion? So like what you do.
Oh, right. So right. But we want to do it with a single boundary. So what you are doing is you prepare E from what? Rough and then. So we want to have a single boundary. Then can we sort of do something in between rough and smooth boundary, and it turns out this is prohibited.
So what happens if we identify the two smooth boundaries? We still get 2 ground states, right?
Identify boundaries.
Yeah, like the same way in the toric code, but only one direction.
Right. If we want to identify boundaries, then you need to specify the rule of like which qubits should be identified and so on, and then there should be no consistent way of identifying. So again, I mean, this identifying is a bit, we need to make it more precise, and then I guess one way of identifying it is like, if I have qubits here sitting on,
They're the same.
then we can say that they are the same. But like, we might be able to say that this qubit is actually same as this one, this is this one, this one, this one.
The same way in toric code, you identify these 2 edges and these 2 edges.
These two and these two? Sure.
So here we only identify.
Oh, okay. Then you just go back to the toric code, right?
No, like a
No,
cylinder.
you don't identify.
Oh, cylinder. Yes. So that's a cylinder. So it's like cylinder with just rough boundary. Yeah.
So you still get 2 ground states.
So let's say how many? Yes. I think so. So right. So the number of ground states actually depend on the configurations of the rough and the smooth boundaries. And then, so for example, if I have some lattice, which is put on the disk, and then if I have rough, smooth, then this one has, lots of degeneracy.
Yeah, that would be a genus.
Right. Okay, so it's actually I think I only have like, so the website said that the lecture should be ending at 4:50, and so the next topic would, I think, take around, 30 to 40 minutes, which is probably too much. So maybe we can finish at this point, or does this sound good, or no, or maybe? Or if you have any questions, just maybe you can ask now.
So in the situation that I was talking about, would you still be able to realize the system without grounds?
So right, so here I had a rough boundary and smooth boundary, but you are saying like you want to, let's say, identify this guy and this guy, this guy and this guy, and so on, to construct some weird geometry.
Yeah, so in the still in the, so that would be, so what you're drawing is a closed surface. That's why it has a cube.
This one, yeah.
But if we only identify these 2, meaning in the same direction, don't identify these, you get a cube that is like an open surface.
Right. So
So you get like an open boundaries operator and a closed loop together.
Right.
That doesn't look like this kind of picture.
So right. Yeah. So I'm not sure if I fully understand your question, but
I guess my question is if we have, realizing anions in the case of in the case you were doing the toric case and here, that requires That requires a closed surface, right? Or no?
You mean which discussion?
So here, like so you showed how you can get like M and E here.
Mm-hmm. Mm-hmm.
So if you have a tube, then you don't get this because like this has to go over the M.
Right. So if I have a tube, then I cannot create a single M particle. I can create a single E particle. Right. Mm-hmm. But of course, the ground state degeneracy depends highly on the like topology of the lattice, including like open or closed or like connected, partially rough boundary, smooth boundary, and so on. It's a very difficult.
It's possible to have rough boundaries on all sides.
On all sides, yes. That is also possible. Mm-hmm. Yes.
Can you always decompose like an arbitrary set of operators in, let's say, on this grid into these excitations?
Sorry.
So
Arbitrary operations into what? Sorry.
into these lines, into these operators, into these
Paths?
strings, into these strings.
Right. So let's see. I'm not sure this is the answer to your question, but starting from the ground state, by implementing some combination Pauli operators, you can reach any eigenstate of the Hamiltonian. And then we have some physical interpretation, such as like creating pair excitations, like creating excitation from the boundaries and so on. But everything can be done by multiplying, applying Pauli operators.
Right, but I was just saying, like, if I give an arbitrary set of Pauli operators on this grid, if we think of them in terms of excitations, that's not unique, though, right?
That's not unique. Right, because, well, yes. I mean, multiplying by a stabilizer operator does not change the energy. So it should give you the same excitation configurations. So there are many there are many different but equivalent way of creating excitations.
But like, in terms of if you have a set of these Pauli operators, X and Z, they're arbitrary, can we always make them into just into these?
Oh, right. Because, I mean...
Even if they're not arranged linearly, they're just anywhere.
Yes. I mean, basically, any Pauli operator can be constructed by Pauli X or Pauli Z operators. And then, I mean, any configuration Pauli X and Pauli Z can be interpreted as like a bunch of open strings. So such an interpretation does exist. Mm-hmm.